Okay. Now our second discrete probability distribution. Probability distribution of discrete events, counts of things, le Poisson, or as I like to say, Poisson. So today we'll just introduce an example of the use of the Poisson and how it's related to the binomial distribution. That'll be a theme throughout the whole lecture, and then we'll talk a little bit about scale dependence, which is just, I guess, a fancy way of saying that experiment size is now more dependent on space and amount of time for sampling rather than number of marbles. And then we'll summarize what I think are the most important things. Okay, so the classic example in textbooks and things that you'll see is from work done by this fellow, a Polish mathematician. I don't know if anybody speaks Polish. I tried it once and got it horribly wrong, and there was someone who was Polish in the audience. Sorry. Anyway, so that guy. And Stern, nice looking guy. Anyway, so he was contacted by a general in the Prussian army, or cavalry, I guess. And they were worried that something had happened and that there was this massive increase in the number of cavalry officers, highly trained, expensive cavalry officers, getting kicked in the head by horses. Right? So this was a dangerous thing back then, just like now it is in today's army with motorized vehicles and everybody moving around at night with the lights turned off and all the other business. The U.S. Army loses from 8 to 10 lads and lassies every year because they put their sleeping bags in the wrong place, because you don't get rained on underneath the truck, right? So anyway, so something similar was happening here. They're walking behind horses and getting kicked, and so they thought maybe they were doing something wrong, or there was something going on. So they asked him to investigate, and what he wanted to do was figure out whether or not this recent uptick in the number of fatalities due to getting kicked in the head by a horse was unusual, could be expected by chance, right? Okay, so what he did is he employed the Poisson distribution and saw that these events, while that year were uncommon, they still followed the normal distribution of numbers of fatalities over the long term. And this was just a sort of an outlying event, but still well within the realm of the particular distribution that it was apparently following. So there was no need, in other words, to change training or anything like that. And sure enough, the next year there was an unusually low number of loss of officers due to frisky horses. Okay, so we just covered the binomial distribution in the homework, but remember that we have a finite number of combinations here, given a finite sample size. And we saw that each term could be described by this equation right here, because that's usually what we were interested in, because these represented outcomes of experiments, and almost invariably we're interested in knowing what the outcome of, say, our experiment is. And this is the way, I suppose, discrete distributions are usually drawn. In this case, the binomial. And you remember in our lab that we had a single, almost smooth line, and that was just because it was easier to connect a bunch of dots in a Mathematica plot than it was to code for these different bars. So that's why You don't see bars in your lab, but but the same thing's going on. We recognize that even though there's a line connecting these two, that the probability density for, say, 0.5 is not some high value. Okay, so let's see what the relationship between a Poisson distribution and a binomial distribution is. It's quite natural, quite tidy. So I'm going to start off by introducing you to obviously a binomially distributed problem, and that is olives falling on the ground below a tree. So we have green olives, unripe olives, and white olives. Apparently there are white olives there in Malta. It's a typo. I just wanted to use the example of olives, so I had to look that up. So this is obviously a tree in Malta. Okay, and this time we're not reaching into a bag of marbles or olives, but instead we're throwing down a quadrat. Okay, that's going to determine our experiment size. Okay, we haven't even predetermined how many we're going to pull out of the bag, so to speak. And then we'll arbitrarily say that that the only marble or olives that count are those that are completely within the grid. So these ones here don't count. So basically we have, I think, an experiment size of 11 and 2 successes if green olives are successful. And we could calculate the probability of this outcome provided we knew the proportion of green olives in all the olives on the ground underneath this tree. And we could think of an extreme example of this in which there are very many olives underneath the tree. And we do the same experiment, and the number of successes, we're just going to say, stays constant, because we want to see what happens to the binomial problem. And what happens, of course, is that n gets very large. And if we keep our number of successes constant, then it must be the case that the proportion of green olives goes way down, right? So in this case here, compared to the previous one, n has gone up, and because we held k constant, p, the probability of successes, has gone way down. This is far more unlikely than in the previous example. Okay. And it's going to turn out, we're going to see that this follows a Poisson distribution, or still follows a binomial, but also follows a Poisson. And in fact, we can go further and say, what if there were no white olives? But instead, we still have the same number of successes. Could we consider this a binomial experiment? And the answer is yes. Why? Because we can know the average area occupied by these olives, calculate the number of possible spaces where an olive could be in this area, and then add that to our number of successes here, and then we could still calculate n and p and k. Okay, so those white olives don't have to be there. We can still consider this a binomial experiment, simply based on knowing the area within our quadrat here. Okay, so we've gone from pulling things out of marble bags now to being able to count things and the probability of events within some piece of space, right? So that's useful. And as well, we can abstract that to counting events in time. We could have some unit of time and count the number of events. So maybe this is, for example, the number of green olives falling during the course of a day or something like that. And if we just define an amount of time here, that can be our experiment size. And if we assume one olive following after another in rapid succession, we could calculate the number of possible olives that would follow in this time, say, and from there calculate n, p, and k. So in a way, these are still binomial experiments, but it turns out there's a much simpler way of counting these. Okay. Because what we notice in those types of situations where the number of successes is very small, i.e. P is very small, and N, or the amount of space and possible N, is very large, it leads to a very flat distribution called the Poisson distribution. So let's see how it's related to the binomial. So here we have the classic binomial distribution that I drew using the code that we worked on in the lab right here. Okay, and it has a mean of 15, and this experiment size is 22. Okay, so and it looks very different from a Poisson distribution. It's much more peaked. Most of the density is around the mean, meaning values near the mean, n times p, are much more likely than extreme values. Whereas we can see with a Poisson distribution with the same mean, values around the mean are less likely, and extreme events are more likely. But look what happens when we do a binomial experiment and calculate the distribution for a large binomial experiment. Here everything is the same, except that now instead of pulling 22 marbles out of the bag, we've pulled out 99. And by keeping the mean the same, that means we've kept the number of successes the same across the distribution here. P must have gone way down. And look what happens. We start becoming less certain about values around the mean, and extreme values become more likely. Okay, and so this binomial distribution seems to converge on what we're calling a Poisson distribution at very high N and very low P probabilities of success. So the Poisson actually is a binomially distributed distribution. It's just a very extreme one in the limit of large experiment size and very low probability of K successes. And we can formalize that mathematically by taking the term for a binomial outcome and taking the limit through calculus as the sample size goes to infinity, and to keep the mean about the same, which is n times p, p correspondingly has to go to about 0. And when we do that and we do all the tricks of calculating a limit, we end up with this answer right here, which is the mean raised to k divided by k factorial times the base of the natural logarithm raised to mu. And of course the base of the natural logarithm comes out because we're dealing with infinities and infinite series, and the number e often pops out as a result. Anyway, so this is in the way a binomial term, but it's for the Poisson distribution. And here we're keeping the mu constant, right? So n can go to infinity and p can go to 0, and we can keep this constant as a result. Okay. So it's kind of a special case of the binomial distribution. But notice the difference. Here we don't have to know the experiment size. We no longer care about n, okay? And instead what we want to know is the mean number of successes, say, that we throw in quadrats or something like that. Okay. And now if we plug in different values of k into that generalized term there, right here, we get all the terms in a Poisson distribution. So this is a Poisson probability distribution. Remember we said that a probability distribution was the probability of all possible events, right? So this is the possibility of the probability that there are 0 olives in the quadrat given the average number of olives in a bunch of quadrats, say. And so on. This is the probability for getting 1, 2, 3, and so on up to k and beyond. I'm not sure what comes after. And unlike the binomial distribution, where the smallest terms were out to the right and describe what was happening down here, in the Poisson distribution, we sort of line up according to an integer scale. Okay, and you'll notice one other important difference here, this ellipsis at the very end, right? So with a binomial distribution, we had a finite number of terms, n plus 1, right? Well, here we have an infinite number of terms. In principle, there is a non-zero probability that k is, 3,000,006,000,000 or something like that, right? Why? Because n is nowhere to be found, and we took the limit as it went to infinity, so k could be anything. But very rarely are values of k like that ever calculated, because they're almost always infinitesimally small. But nevertheless, this will introduce a challenge in calculating probabilities that we'll look at in a little while. Now, we talked a lot about parameters. Remember that the binomial distribution had 3 parameters, n, p, and k. Here it has a single parameter, and that is the mean. As long as we know the mean, we can calculate the probability of a Poisson outcome, okay, for a given k. It also has another cool property in that the mean is equal to the variance. Remember we said that the variance of a binomial distribution was always greater than the mean. Actually, we said it was always less than the mean, right? And here it's equal, okay? So if you're wondering whether your data converges on a Poisson versus a strict binomial, you can check the relationship of the mean to the variance. Now, oftentimes we don't have the parametric value for the entire population. Remember, these are Greek letters, so they're population values. Instead, we estimate them via some sample here, so we'll call this bar k, or k bar, and the sample variance notation that we've used. Okay. And we can use these to see whether or not a distribution conforms to Poisson expectation, simply by taking what's called the coefficient of dispersion, which is just the ratio of the variance over the mean, usually the sample in both cases. And the closer it is to 1, the more confident we can be that we have a Poisson situation, right? So let's do an example here. I guess another important thing is, because we don't consider n experiment size, it matters in a way in that the size of the quadrat determines what the Poisson parameter will be. Remember, the Poisson parameter is the mean, which we approximate via the sample mean. And so if we had bigger quadrats, clearly our average number of green olives in the quadrat would increase as well. So we have to specify how big our quadrat is, say if we were writing a science paper or something like that. Okay, so that matters. So that, in a way, is experiment size, right? But we call it scale dependence. And this goes for increasing amounts of time, too. Say if we're measuring, frog croakings or something like that. Okay, so let's see. Okay, yeah, it looks like we're going to do an experiment here. We got 1, 2, 2, 4, 5, 5. Those are our data. Right here, these are all our Ks. We take the average, and we take the variance. We calculate the variance using the sample variance that we learned how to do in chapter 2 or whatever it was, right? And then we just make a ratio out of them and see what the value is. Now here, it's about 0.94, which is pretty high, so we might strongly suspect that our data are Poisson distributed, and that the olives under the tree follow a Poisson distribution, okay, in space. Now, just how high does this have to be before we can be confident that it's Poisson and not something else, negative binomial or something like that? we're going to spend the rest of the semester learning how to put bounds on our estimates like this and measure how confident we can be given some statistical value. So this is a statistic, obviously, a descriptive statistic of data called a coefficient of determination. And we'll learn how to put bounds and confidence limits and stuff like that around these values later on. But for right now, if we saw that value, we'd think, I think it's Poisson distributed. Now, can you think of ways in which the distribution of olives on the ground might deviate from Poisson expectation without increasing the number of olives that you see here? What if we...
If maybe you have too little in one box, but then too many?
Yeah, exactly. So the data could be clumped. There could be like really healthy branches of olives and really kind of scraggly branches, and so some dump lots of olives, some drop few, so we have 10 here, 2 here, 10 here, 2, or something like that. Now what would that do? The average would be the same. We haven't changed the number of olives, but the variance would jump up. The numbers are much more variable, right? And we could do the opposite. We could rearrange these olives in such a way so that there was an equal number of olives in each one. What would that do? Well, again, the mean would stay the same, but what would happen to the variance? There would be no variance. There would be no variation. It would plummet towards 0, right? And so your value would once again, and you would suspect what from that? That maybe the olives are distributed much more evenly than expected under Poisson expectations. Whereas in the previous case that you mentioned, they're much more clumpy. Right? And that's kind of what you see in nature. Sometimes you can have small quadrats out on the reef and you'll see what looks like a Poisson pattern, but if you use bigger transects, all of a sudden things will start getting clumpy, and that's just the way nature is. It's very scale dependent. Okay. Now, if it was, let's see, the variance was less than the mean, remember we said that was an indication that it was binomially distributed, and maybe that would be the case if we even things out a bit. There's another common distribution called a negative binomial. You don't have to know that, but it's often characterized by a very high variance compared to a Poisson, much greater than 1. Anyway, so these things tell scientists stuff about what's going on in nature. Okay, so we looked at that. Okay, so how would we use this to solve simple problems and calculate Poisson probabilities? Well, let's say we threw out a quadrat, we knew the mean number of olives in each quadrat, and our quadrat had 3. Well, then we would simply find the term here for 3 successes, or 3, k equals 3. This is for 0, remember, so it's the 4th term. And we put it there and we just solve that. That's fairly simple. And then the other type of problem we encountered with the binomial distribution is when k is less than or greater than something. And here we just sum over all the terms that are appropriate. K is less than 3, therefore 0, 1, and 2. So we sum over the first 3 terms. We could have used summation notation right here, right? And put in a k. And the final one, which is slightly different than the binomial distribution, is the issue when k is greater than some number or greater than or equal some number. Because there's an infinite number of terms here, the only way we can solve the equation is to take the one complement of this. Of k is less than 3. Okay. So I guess that's that one right there. Okay. So that should give you a pretty good guide for solving most of the homework problems right there. Okay, so to summarize then, Poisson, you know it's a discrete distribution, and it's described by a single parameter, mu, which is the mean, which we often approximate using a sample mean, which we called k bar. Often uniformly and randomly distributed rare events are distributed in Poisson fashion, and by uniformly and randomly distributed, that often means so distributed in space or time, right? Through time, or on a surface, or in the air, or whatever. Okay. Third is the mean and the variance Poisson are equal, or at least ideally they're equal. If you're sampling, there'll be some slop. And the coefficient of dispersion measures this via the ratio of these two values, and it should approximately be 1. And finally, the binomial distribution converges on the Poisson when n is very large and p is very small. And well, we took the limit, we did this, formally and properly. You actually converge on a Poisson distribution very quickly, even when n is just on the order of like 50 or 60 or something like that. So it doesn't have to be thousands or millions or anything. So even when it's about that big, 50 to 70 or 100, say, and p is relatively small, you're probably looking at a very Poisson distributed distribution, a very sort of deflated looking binomial, very fat tails. Okay, so depending on the data you have, then you may want to use the binomial equations to solve the problem, or you might want to use the Poisson. So you'll see that maybe even on the homework for this chapter, I'll give you questions that you could solve either way, and you'll get slightly different answers, and you can even check and do it both ways and check for yourself. Okay. So any questions? Okay then. So I wanted to finish off with an example of the use of Poisson distribution. So I said that the Poisson often measures rare events, and that usually means that the mean value then is rather low. If you have a mean value for your quadrats of 150, that's probably not Poisson distributed. These events usually have to be sparse and scarce. That's usually how they're measured. So corals, I guess, are under a lot of threats, obviously, and one of them is bleaching and destruction of habitat and things like that. One of them is coral disease, which seems to be on the rise and correlated with all these other stressors. And so there's an effort to place the study of coral disease in kind of a modern epidemiological context rather than simply going out and counting colonies that are diseased. And one of the premier ways that corals are assessed for disease status is the prevalence of the disease in a population. Right? And prevalence just means the proportion of colonies that are diseased compared to the all the colonies in the area. So you go out on a transect, measure 100 colonies, 10 of them are diseased, the prevalence would be 0.1. Okay? Sometimes called the point prevalence because you just measure it at one single time. It differs from incidence, which is the acquisition of new infections over time. There's all these other things that have been worked out by epidemiologists in other fields, plant pathology, veterinary medicine, human medicine, etc. So this is still sort of in its infant stages. So this is being used a lot, simply the prevalence. And when this prevalence goes down, it's often thought that, well, the population is getting healthier. But what I noticed is that's not always the case. And it has to do with the fact that diseases are often Poisson distributed. Okay, so if we imagine a coral colony, I'm going to say in plan view, right? We're looking down at, say, an encrusting coral, so it's very simple. And there's a rain of disease propagules landing on them. And this is a coral colony of, say, 1,000 polyps of, some small size. And one of them gets infected, right? And then later on, there's a disease lesion around that. But we know that at one time it started as a death of a single polyp, which received a disease propagule because it's fanning out. And so we could think of this as a binomial distribution problem, right? We could count the number of polyps. We could say that's n. The number of successes of the disease is maybe 1 or 2, something like that, right? And assuming some low p or value for the number of infected polyps versus the total number of polyps in the colony, we could probably calculate the binomial probability. But it's much easier to calculate the Poisson probability. Why? Because these are very rare events. They're distributed randomly. If you count the variance and scale it by the mean using the coefficient of dispersion, you'll see that it conforms quite well to Poisson expectations. And so what I noticed was that, what I noticed, it's because I drink a lot of Diet Coke. So I was getting some coins because the dollar function on the machine there didn't work, as it often doesn't. And so when I pulled the coins out, I spilled them on the floor, right, like so. And I thought, and so I'm picking up, I thought, because I've been working with this disease problem, I thought, cool, coins are like disease lesions on the tiles, right? So I thought, what's the prevalence of coins on my tiles? This is what scientists spend their time doing. And so I calculated it, and I guess maybe I had some over here, something like that. And I can't remember what I calculated, but it was something pretty low for a tile. I think it was like 0.38 or something. But then I realized, what if I had bigger tiles, right? What if instead of 12-inch tiles, Marine Lab had gone all out and got some really nice looking 18-inchers, preferably without asbestos. And I realized that the prevalence would change. All right, so now, I guess I'll make this a little square. The big square, it was about, and this, I guess, is about 0.75. So lo and behold, prevalence of diseases, at least lesion-forming diseases, in a population, the change in that prevalence doesn't solely depend on the health of the population. It depends on how big the colonies are, right? And for some reason, no one's ever noticed this before. But look what happens when corals get killed by disease. What happens to their size? They become smaller, right? And look what happens to the prevalence of disease when colonies get smaller, even though the distribution, number of lesions, and spatial arrangement of those lesions is completely the same, right? So I was thinking, maybe, I must have counted 80 papers in the literature, that maybe this is happening rather than diseases getting better and stuff. So what I realized was is we could model this as a Poisson process. So the probability of being diseased I guess the probability of being healthy is the probability of having 0 lesions, right? And we remember from the Poisson series, although we've just seen it, that is, help me out, 1 over e to the mu, right? So if you have 0 lesions, you're healthy. Right? And if you're diseased, and remember there's an infinite number of terms in a Poisson process, right? So what we have to do to calculate the probability of being diseased is 1 minus this probability of being healthy. Like so. And this depends on the Poisson parameter, the mean. And of course the mean goes up, right, as the colony gets bigger, it's more likely to have more lesions, right? And so what I did was I just put this in Mathematica, and I plotted sort of the average coral area, let's call it like that, average area, the prevalence against that average area, right, for some given mean number of lesions per unit area, whatever. And what I found is that, and if this is 1, i.e. 100% prevalence, this is 0, what happens is you end up with a curve that looks like this. And this is weighted by the size class distribution in a population. Here I'm assuming they're all the same size, either all small or all large, i.e. this is the average size and the variance in those populations are 0. But we could do the same thing. So this is when variance in area is 0. And it looks something like this when it's greater than 0, and it starts converging down here. But anyway, the point is that the difference between 0 and 100% prevalence is pretty big range for diseases. And so people are starting to use this Poisson measure, assuming Poisson distribution, like so. And I found out later this had all been done for corn plants back in the 50s, as things often are. You know, the agricultural scientists got lesions on leaves and figured, well, it's probably Poisson distributed. You know, they didn't have great computers back then, so yeah, this is a pretty simple way. Anyway, so boom. I showed this at the Coral Reef Conference, not last time, but the time before. And yeah, some people were really quiet. There's apparently an initiative, you know, on the tune of, you know, a couple $1 million to make a worldwide database for prevalence of disease. And I asked, you know, is anybody recording the coral sizes or the coral size distributions? So you know when there's a change, it doesn't just mean that the corals change average size. And they said no, and a couple people came up to me and said, oh, but it's the number that you counted. And, you know, I said, no, I'm so sorry, no, that's not it. Anyway, so an example of using very simple ideas about the Poisson distribution to figure out something that is of interest to other people. Okay, so any questions? Okay, well then, I'll see you Tuesday, and we'll go, remember no lab, we'll go over the Poisson homework and do the remainder of the discrete distribution chapters, the last 2.
So we're going to lecture 5 and 6.
Right.